Well, as promised, here is some help with working through the questions of 9b. We start off with a question where you are given a digraph and you need to produce a matrix, an adjacency matrix from that graph. Now, I already started it for you. We've got 5 nodes, A, B, C, D, E. A, B, C, D, E is down there on the right, but you also want to put A, B, C, D across the top. And then for every way of getting from one place to another, we put a 0, 1 or 2. A to A, there is no loop, so that's a 0. A to B, there is 1, which is there. A to C, there's 1 down there, that's 1. But A to D, there's no way of getting across, and A to E, there is no direct way either. B to A, there's 1 going that way, but not going the other way, so that's 0. B to B is 1, that is a loop. B to C, there's 1 going from C to B, but not B to C. B to D, there is 1, and B to E, there is nothing, and so on. You'd fill that in if you wanted to. And there is actually the correct answer, so you can see that we've got pretty much the same answer on the first 2 lines. Good. And that takes us to the next kind of question. There's several of those in the textbook, and question 1, I've just done one of them. Question 2, I've chosen one of them. This time we are asked to create the digraph from the given adjacency matrix. So we know there's 4 points. Now the way to do this normally is to put them in roughly into circular clockwise order, P, Q, R, S. Apart from anything else, it helps with marking. P to P, there's nothing. P to Q, there is 1. So don't forget we need to put an arrow on there. And P to R, there is 1. And your answer won't look the same as this. If you start somewhere, you'll be differently. And P to S, there is 1. Q to P, there is 1. Now we don't just we could just put another arrow on that line facing the other way, but that is the way to do that. Q to Q, no loops. Q to R, there is 2, so we need 2 ways. Q to S, nothing. R to P, there is 1. Hope we don't run out of space here. And R to S, there is 1. Bit messy. And S to R, there is only 1, so that's alright, we've done it. She'll put the arrow down there. The answer, which is probably a bit tidier than mine, or an answer, is there. Much the same thing. They went round the outside. Not quite sure why they needed to. We certainly didn't. That's because they went P, Q, R, S, whereas we went P, Q, R, S. So maybe they should have done it what we did. Now, moving on. This time we have Joni, Ian, Dylan and Joshua, 4 teachers, and the school's got 4 classes to fill: maths, English, geography and science. So we have to do an allocation. Now this is just creating the bipartite graph. There's no Hungarian algorithm in this yet. So just need 2 columns in the people and things, J, I, D and J, and then down the side maths, English, geography, science. And then we link up. Joni can teach English or geography, so we'll have a line going down there and a line going down there. Ian can teach maths or science. Dylan can teach English or geography. Oh, clever chap. Joshua can teach geography or science. So we've done part A. Explain why Joshua must take the science class. Well, now, who's going to actually do what? We can do this by elimination, and the first thing that you need to notice is that Ian is the only person who can teach maths, which means that Ian will have to teach maths. Know the problem. Mark it in. Selected. Ian teaches maths. Now that means that Ian can't teach science. So that one, Ian to science, was not going to be used. Now Josh is the only other science teacher. So already we have decided that Joshua has to teach science because Ian has to teach the maths, Joshua has to teach science. So we've answered that question. Right, two different allocations of teachers to subjects. Well, we've got Ian to maths, Joshua to science. We've still got to give Joni and Dylan a job. Now, it doesn't actually matter. We could have Joni to English and Dylan to geography, or we could have Joni to geography and Dylan to English. So those are the two options. So we've got I to M, Josh to science, Joni and Dylan can teach either English or geography. That effectively gives you two different allocations of teachers. All done. So that's just creating a bipartite graph and analysing it without any weights. That's the answer in the textbook, which must be the same as ours. Now we are going to work on a cost matrix and use the Hungarian algorithm to give the minimum cost. So we've got 4 maybe people, W, X, Y, Z, and 4 tasks A, B, C, and D. First thing you do is look at each row, find the smallest number and subtract that number in the row. 110, 95, 140, 80 on our first row. The smallest number is 80, so we take 80 from each of those numbers and we're going to get 30, 15, 16 and 0. Smallest number in row X is also 80, so we do the same there, finishing up with those numbers down there. Smallest number in Y is 75. Smallest number is 75. That comes off each of the Y numbers, and there's each of the Z numbers. And then you try and cross out all the zeros with less than 4 lines. Well, that's easy, straight down there, no problem. So that table then gets transferred to the next stage. So here we are, come in there, that's what we just did. Now we look at each column and we take the smallest value from each column. The smallest value in this column is 25, so 25 comes off each of those numbers there and produces 5, 0, 25, 5. Smallest number in column B is 2, so 2 comes off each of those numbers, so that's that one done and that one done. Smallest number in C is 50, so we take 50 off each of the C numbers and finish up with there, and these last ones are already 0. Can you cross out the zeros with less than 4 lines? Yes, you can. I've done that there. 1, 2, 3. Don't worry about that circle on that one, that comes on the next slide. Identify the smallest uncrossed number. Well, it's 1. Having identified the smallest uncrossed number of 1, we then add that to each of the numbers which are crossed out twice. So there is 1 here and 1 here. They've been crossed out twice, so they're going to have a 1 added to them each. And the other thing you do with your 1 is you subtract it from each of the uncrossed numbers. Well, there's a 5, 13, 10, 25, 15 and the 1 itself. They all come down by 1, so that's those numbers all down in that table down there. Check that 4 lines are now needed, which hopefully they will be. I'm going to do those 3 to straight away, see if I get rid of as many as I can, and those 2. But I have to use 1 line there and 1 line there to get rid of the rest. So I do need 4 lines. So I can now apply the Hungarian algorithm. That's the table again with just the zeros in it. Now you can create the bipartite graph from the 0 cost items. Already been done for you. W to D, X just goes to A or B. Y goes to B or D, B or D, and Z can go to A, B or C, A, B or C. Looks a bit messy now. Go to the next slide and have another look at it. Do what we did before. Choose a different colour. W must be allocated to D because W doesn't do anything else. So there we go, W gets allocated to D. The only other person going to D is Y. Y can't do that now, so that means that Y has to go to B. Continuing that, X could have gone to B, but he can't anymore, so X will have to go to A, and Z Finally, let's go to C, and that is our final allocation. Then we do the cost. W to D was 80. Y to B was 78. We did the 105 and we did the 135, and those four numbers add up to 398. So that is the cost of that allocation. Alright, there's plenty more examples in the textbook of working through all these three kinds of questions using digraphs, bipartite graphs, adjacency matrices to solve matching and assignment problems using the Hungarian algorithm. Exercise 9b. Please do the remaining questions. It'll take a little while. Worth doing.